Hi everyone. Okay, so before we begin today's class, if you haven't already gotten a chance to look at the ebook, it contains most of the important formulas for the AMC 1012, which is coming in less than a week now. So it contains formulas, concepts, and while making the book, we analyzed many of the past papers, and then now we've created this book, which will hopefully help you review most of the important concepts and formulas, many from these classes. Okay, so while you were waiting for some people to join, it looks like some people still haven't joined. So you can try the review problem. This review problem is really a really cool application of similar triangles. So again, this problem, the key idea is that we've got two angles equal, so we want to construct some kind of similar triangles here, and I'll talk more about the solution in some time. Nice application of similar triangles. So basically, we have this quadrilateral here when we have that AB is 8, BD is 10, and BC is 6, and we're given that we want to find the length of CD. So CD, this obscure length. And we also know that these angles, the diagram already marked it for me, which is nice. These blue angles are equal, and these red angles are equal. So what does that tell us? Well, if we have two angles equal, what does that sound like? Remember, AA similarity. If you have two angles equal in two triangles, the triangles will be similar. So in this case, the blue and red angles are common in both of the triangles. But wait, this was actually not part of the diagram. I should have removed it, but this is actually not part of the diagram given in the problem. This is just something added. So in this problem, we have two angles common, but so that means we probably have similar triangles. So what two triangles are similar? Well, ABD and, well, there's no other triangle because two angles are equal, but there's no third point to the triangle. So what do we think? What do we do now? So we somehow have two angles equal, and we want to somehow form a similar triangle because two angles AA similarity is very powerful. So what do we actually conceive from here? Well, what we can actually do is we can actually extend both of these lines. Because by extending these lines, we now have constructed two similar triangles. And the triangles that are similar are A, B, D. So ABD is similar to DCP. So ABD is similar to DCP, right? Because by extending these lines, we've now constructed two similar triangles, which is very, very powerful. So what do we know from here? So, well, remember, similar triangles has lots of useful information. It tells us that the angles are all equal and that the sides all have the same ratio. Always remember that there's two useful things you can extract about similar triangles, the angle condition and the side length condition. So how can we extract the angle condition? Let's start with the angle condition. Well, we already know the blue angles are equal, the red angles are equal, and that means, well, these green angles have to also be equal. This green angle and that green angle, right? So now that we extract the angle condition, what do we know about this? Now we've gotten some more angles. We can actually see that, well, these two side lengths are equal. Because these angles are equal. Because two angles equal means two sides are equal. So now that we know these angles are equal, we know these two sides are equal. Meaning that these two sides are equal. So this is 10. Hopefully that makes sense. Because if two angles on the base are equal, then the side lengths will be equal. And by knowing these triangles are similar, we got the angle condition. So now 10, 10, 8, and then this has to be 6 too. So now what can we do? Well, now the key thing to actually try to understand from here is that in order to find the length of CD, now we need to look at the other condition of similar triangles, the length condition. So from here we can see that the ratio of sides BA, so the ratio of BA over BD is going to be equal to the ratio of CD over CP. So I'm just going to write that out. So we have that AD over, sorry, I probably shouldn't have written in such a thick pen, over AB is going to be equal to, sorry, not AD over AB. We have that AB over BD is going to be 4/5. AB over BD is also going to be equal to CD over PC, right? And AB we know is 8, BD we know is 10, CD we don't know. That's what we want to find. We want to find CD, right? So this is going to be CD over PC. Well, by our isosceles triangle condition, we got it's going to be about 16. So from here we can see that the 128 will be equal to 10 CD times CD, which means CD is 128 by 10, or 64 over 5. So the answer is just going to be equal to 69. And this problem is really clever in the sense that what we have to do is we have to think that two angles are equal. That means the triangles are probably going to be similar. And that by knowing the triangles are probably going to be similar, from here we can see that because we know the triangles are going to be similar, the ratio of the sides are going to be equal, and the angle conditions are also going to be equal. So now that we extracted both of those information, we got the angle conditions, we found that the angles are equal, we found that the PP is going to be equal to BD, and then we use the side length condition, and we wrote the ratios out, and from there, we easily solve for the length of CD. So now we're going to move on to today's topic. So we'll start off with the very basics. I'm sure all of you know, circle has the area of pi r squared, circumference 2 pi r, and area of a sector is just going to be the degree of the sector divided by 360 times the area, and the length of the arc is the degree of the sector times the circumference of the circle. And we already discussed this in the AMC math counts and AMC 8 classes. You can go check that out for more information. But for now, we're going to move on to some more advanced techniques. But we also covered these in the AMC math counts classes. Go check those out if you're more new to these concepts. But let me just quickly overview what's going on here. Basically, if you have some angles A here, here, and here, then these angles are going to be half of the angle formed at the center. So all three of these angles, or any angle, it can be something like this too, they're going to be half of the angle formed by the arc here, which is also equal to the angle formed here. So the angle in the arc is double the angles on the sides. Also, we have the inscribed triangle with diameter on one side is always going to be a right triangle. This is just a direct consequence of the previous condition. This is 90. The arc has to be 180. Yeah, so the right triangles are described in circles. We already discussed these more in detail. The AMC math counts classes are more basic classes, so you can go check those out. But for now, let's try some simple problems first. And we're going to start off with some simple problems in the beginning of the class. And towards the end of the class, we're actually going to explore some very challenging problems. So let's start off with some simple examples. The diameter of circle radius 2 is extended. So radius 2, this is 2, that's 2. Extended to a point D outside the circle so that BD is 3. So this is 3. And we also know ED is 5. So 5. And then we're saying that segment AE intersects a point circle between point C between A and D. So we have segment AE is intersecting the circle at this point C here. And then we're saying that we want to find the area of this here. So we know that C is going to be on the circle, right? C is going to be on a circle. And we know that this is going to be 90 degrees, right? Because this angle, the angle here is going to be half of the angle formed by the arc. The angle formed by the arc is always going to be double the angle formed in the inscribed angle. So since this is 180 degrees, this will be 90 degrees. We just discussed that property on the previous page. Diameter means 90-degree angle. So very cool property about circles and diameters, gives us information about 90-degree angles. So definitely something to be on the lookout for. We also know this is 90. We're given that in the problem too. So now I'm trying to find the area of ABC. Firstly, what's the ratio? Well, we can actually see that triangles, we can see the triangles ACB and So ACB we're given is similar to ADE because one angle is common between both of the triangles, and we also know two angles are common actually. We know that one angle is common between the triangles, and this one angle is 90 degrees for both of them. So by AA similarity, the triangles are similar. Okay, so now that we know the triangles are similar, how can we find the area of ABC? Well, first note that the area of triangle ADE is simply equal to 5 times 7 divided by 2, which is going to be equal to 35 over 2. So the area of ADE is 35 over 2. Now, how can we find the area of ABC? Well, in order to find the area of ABC, well, we know the triangles are similar. So now we need to look at the scale factor between the two triangles. So we can see that the ratio of the scale factor between the triangles, well, notice that the hypotenuse of the large triangle is simply equal to the square root of 5 squared plus 7 squared, which is equal to square root 74. Right? So therefore, the hypotenuse of the large triangle is square root 74. The hypotenuse of the small triangle is 4. So the ratio between the areas of these two triangles is going to be 4 over square root 74 squared. Right? Because we just do the side length divided by the scale factor squared. Area ratios side length squared. We discussed that in the previous class, remember. So that means the ratio of the areas is just going to be 16 over 74. Which means the ratio of the areas is 8 over 37. Right? Okay, so now that we know the ratio of the areas is 8 over 37, now what can we do? Now, we can just multiply this ratio by our side length. So from here, the problem becomes relatively straightforward because we can just, in order to find the ratio of the areas, we really just need to multiply it out together. So by multiplying this out together, we just do this times 37. We see that we're going to get an answer of 35 over 2, which is going to be the area of the large triangle, times 8 over 37, which is going to be the ratio of the areas of the smaller triangles. And then we get that we can cancel some terms out. This is equal to 140 over 37. So that's the area of ABC. So in general, the types of problems you want to, the circles gives us good properties about angle tracing. So that's a good thing to keep in mind. And this, okay, let's go on to the next problem. So this is another cool problem. Basically, we have externally tangent circles with centers A and B, have radius less than 5. So these are good problems because they combine similar triangles in the previous class and the circles concept we're learning in this class. A line externally tangent to both circles intersect right AB at point C. What is BC? Okay, so this has a length of 3. This is 5. This is 8, right? So remember that we actually know, we discussed this in the AMC class, that when we have a circle and a line that's tangent to it, this angle is going to be 90 degrees. So that means this will have to be 90 degrees. This will have to be 90 degrees, right? Because that's a tangent property, 90 degree angles. Okay, so if we know these are all 90 degrees, what can we do from here? Well, if BE is 3, then we can see EC is just going to be equal to 3x, right? And similarly, we know that DC, the whole thing, is going to be, or I should have actually done it slightly differently. Let's just say that BC has length of x, right? Then AC will have a length of 5/3 x, because the ratio of triangles BEC to ADC is 5/3, because we know the side length ratio is 5:3. The ratio of the side lengths is 5:3, so that means the ratio of the side length BC to side length AC is also going to be 3:5. So that means you can see that AC will have a length of 5/3 x, right? And from here we can see that AB will just then have a length of 5/3 x minus x, which is 8, meaning that 2/3 x is 8, or x is 12. So x will be 12, and that's the answer we want to find. Again, the key idea here, tangents are always 90 degrees. Keep that in mind always. So you draw 90 degree angles. We saw that if these are both perpendicular to the line DC, then the side lengths are parallel. Because if these are both perpendicular to one side length, then the side length has to be, these two side lengths have to be parallel. Because they're both like hitting a 90 degree angle to one common line. So they're parallel. It means the triangles are similar, which means the ratio of the side lengths are equal. Then we saw that 5:3 is 8 plus x to x, and then we can solve it from there. Okay, so now let's take a look at our next problem. So I'll give you some time to try this on your own. So basically we have 7 cookies of radius 1, and they're cut from cookie dough, And then neighboring cookies are tangent and are all left except the center cookie. And then we this has this big circle and we subtract the area of the smaller circles. And then after that, after subtracting the smaller circles, we take this graph and then we put it together and we make another circle. We want to find the radius of this circle. So I'll give you some time to try this on your own, and I'll give you a hint. Whenever in circle problems, you want to draw the lines from the center to the tangency points. Very helpful technique. Useful in this problem and several problems we're going to do down the line. In circles, draw the center to the tangency points. Draw all possible radii that can be useful to you. Draw 90-degree angles, connect circles. It's always very useful and give you so many new properties to work with. So I'll give you some time to try this now. As you can see, I drew out some lines here. And basically what these lines are telling us is that by drawing all these radius ones, we now can actually try to find the larger ratio. And like I said earlier, connect centers, connect radii, very powerful technique for the simplest of problems like this one, and for the more complicated ones we're going to do later on in class. So this is one. So then we can see that the radius of the big triangle, the big circle, there's no radius of a triangle, is going to be 1 plus 1 plus 1, which is 3. So the radius of the big circle is 3, right? The radius of the small circle is 1, right? So what's the area of the big circle? The area of the big circle is simply the radius of the big circle is just going to be 3 squared times pi. And we can see that the radius of the big circle is just going to be, the area of the big circle is 9 pi. Now we're basically taking everything, all these small circles, and removing them from our big circle. So the area of each of these small circles is just going to be 1 squared pi, or pi. So the area of 7 of these circles is just 7 pi. So the area of the remaining is just going to be 9 pi minus 7 pi, which is just 2 pi. So that means we put, if the circle is area 2 pi, what's its radius? Well, we know that r squared pi is 2 pi, or dividing by pi on both sides, you get r squared is 2, or r is root 2. That's the solution for this problem. It was a pretty straightforward problem, the main idea being connecting circles, connecting tangency points, very helpful technique. Okay, now let's move on to this problem. This one is kind of a troll problem. Basically, we've got n congruent semicircles that are drawn. And their diameters cover. And their diameters are covering this large semicircle with no overlap. Let A be the combined area of all these small semicircles, and B be the region outside them, inside the big semicircle. So A is the region of all this stuff, and B is the white area here. And we're given that the ratio of A to B is 1 to 18. What is the value of n? And n is, again, the number of congruent semicircles on the bottom. So the very thing to not get trolled on is that the ratio of A to B is 1 to 18, not the ratio of the gray to the whole thing. So the ratio of the gray region, all this gray region, to the white region inside the semicircle is 1 to 18, not the whole semicircle, just the white part inside it. So that means if this gray region has an area of x, then all the white region inside the semicircle will have to have an area of 18 times x. Okay, so what can we do from here? We can actually see that the ratio of the small gray semicircle to the large semicircle is 1 to 19. Okay, so the ratio of the small semicircle to the large semicircle is 1 to 19. Then what? Well, then we can just look at the area ratios and actually calculate n. And I'll give you So what do you think we can do to calculate n from here? I'll give you some time to think about that. Okay, so basically the key idea is that the ratio of the great semicircles to the overall thing is 1 to 19, because 1 over 18 plus 1. So the ratio of the great semicircles to the whole thing is 1 over 19. Let's explore what it means. So we have n of these semicircles, and what is the ratio of, think about this question. What's the ratio of just one of these semicircles to the whole big semicircle? Well, one semicircle, let's say, has a radius of 1, and the big semicircle will have a radius of n, because there's just n of these semicircles put together. So the big semicircle has a radius that's n times larger than that of the small semicircle. So the ratio of the area of the big semicircle to the small semicircle is n squared. So the ratio of the area is n squared. Then what do we know? Well, the thing is, if the ratio of the areas is n squared, we can see that the ratio of one gray semicircle to the whole big semicircle is 1 over n squared. But remember, there's n of these semicircles. So that means the ratio of all n gray semicircles to the whole big semicircle is 1 over n squared times n. Which means this is going to be equal to 1 over n. And remember, we found that the ratio has to be 1 over 19. So what must be n be then? 19, of course. So 19 is the answer. Be very careful of the beginning condition that it's the part outside. So now let's take a look at the next problem. This is another cool problem that involves both triangles, similar triangles, and circular techniques. So in this problem, we have two circles, radius 5. And the reason you might be thinking, why am I marking all these random radii? The thing is, not all radii are useful. If you think about a circle, there's infinitely many radii you could possibly choose. There's a few key select radii that are actually useful to us. So in each of these circles, we draw the useful radii. So for example, this radii and this radii, they're both useful radii because they're connecting center to other useful points. You don't just draw all the radii because that would be impossible. So we can see here that after drawing these useful radii, we now have some new information. Now we know that this whole length here is 10. This green length is 10. Okay, so if this green length is 10, what else do we know? Well, if this green length is 10, what other information have we not used in the problem? Again, a key strategy in this types of problems, look for the information you haven't used. Great problem solving technique. When you're stuck, look at the information you haven't used. What is the information you haven't used? Internal tangent to a circle of radius 13. We haven't used the fact that the big circle has a radius of 13. And again, the big circle has infinitely many radii, but we don't need all of the infinite radii. We just need a few key select one that gives us useful information. So what radii do you think we could draw here from the big circle? What radii are the ones that you think we should draw for the big circle? The ones we should draw are these two radii. Because after drawing these two radii, that kind of aligns in and gives us even more information to work with. So if we know each of these red lengths are 13, so if we know that this is 13 and this is 5, then we can see that this part here is just going to be 8. And this part here is also just going to be 8. Because 8 plus 5 is 13. So 13 is going to be the big radius of the circle, and the radius of the smaller circles is 5, so the two side lengths of the triangle are 8. I already gave it away. Two side lengths of a triangle. Yes, we have another triangle in our figure. This is actually a triangle with side lengths 8, 8, and 10. Okay, so now we have a triangle with side lengths 8, 8, and 10. Because of these crucial information the radii gave us. So now what do we want to do from here? Now, how do we find the length of AB? Well, notice that the length of AB, how can we find out the length? Well, let me just clean up the diagram a little bit. How do we find AB? Well, notice that if you draw the line AB, triangles, sorry, it got erased somehow. if you draw a line AB, we actually have two similar triangles. The triangles that are similar are this green one here and the big blue one here. This green triangle and blue triangle are similar, and by a ratio of 8 to 13, meaning that side length AB will be equal to 13 over 8 times 10, which is equal to 130 over 8, which is equal to 65 over 4. So that means the answer is just going to be equal to 69 because it's asking for the sum of the numerator and denominator. So again, the key idea was looking at the radius, drawing the useful radii, because we cannot draw all the radii. Draw the useful radii that gives us actual information that will help us. Use that, find information about the triangle, and then the problem is pretty straightforward with similar triangles. Okay, so now let's take a look at the next problem. 3 circles, mutually tangent radii. 2, 2, 2. Again, I'm drawing the useful radii. The useful radii are the ones that are connecting tangency points. Drawing the 90-degree angle, the ones that are tangent to circles. Okay, so I'll give you some time to try this, but again, the key idea, draw the useful radii, see what information you can extract. The key part in this problem is what is this weird region in the middle? This weird region in the middle is somehow we have to find it out. So now I'll try and I'll come back to you with the solution in a minute or two. Okay, so it looks like some of you have some good ideas. In order to find the area of the 3 gray circles, we need to find the area of this equilateral triangle in the middle here. We need to find the area of the equilateral triangle in the middle and the area of the other sectors on the outside. What's the area of this equilateral triangle in the middle? That's just going to be equal to 4 squared times root 3 over 4, which is equal to 4 root 3, okay? So that's the area of this equilateral triangle. Now what's the area of these regions here? Well, the area of these regions, how can we calculate those areas? Well, this angle is 60, this angle is 60, this angle is 60. What is the area of these regions here? How can we calculate those areas? Well, notice that these 3 circular arcs on the outside have a 300-degree angle. So the key idea is that since equilateral triangle has an area of 60, this will have an angle of 300. So that means the area of one of these, let's just say the area of this region here. This region here. So what's the area of this region here? It's going to be equal to 300 over 360, because it's a 300-degree arc, times the radius squared, so times 2 squared pi, which is equal to 5, 6 times 4 pi, equals to 2, 3, just 10/3 pi. And then if the area of one of these green regions is 10/3 pi, the area of 3 of them is just going to be 3 times this, equals 10 pi. So the area of 3 of these regions is 10 pi, the area of the middle triangle is 4 root 3, and the area of the total area is just going to be this. That's the solution for this problem. Very clever idea of finding the area of 3 arcs, looking for the equilateral triangle in the middle to get that tiny slitter area here. It's kind of weird to find. Okay, so now let's take a look at this problem. So this problem, again, another cool application of drawing the select radii. This time, I'll let you try to draw the radii on your own, which is probably going to be hard. But just think of what radii can you draw. Of course, you cannot draw every radii in the circle, but think of itself which radii to draw that will give you useful information. I keep muting myself. But basically what I was saying is that we want to connect the tendency points radii. So connect all these equilateral triangle tendency points radii. And what does that tell us? By connecting all these radii, we now have a bunch of equilateral triangles. And to find the area of this shaded region, we need to find the area of the large circle and subtract the area of the smaller circles. And to find the area of the large circle, we need to find the radius of the circle. And for that, we're going to need some length tools. So how do we find the radius of the large circle? This is 1. Then we can see that this will be root 3 and this will be root 3. Right? Because of the 3069 triangle property. I should probably explain a little bit. So this is 1. We see that this is 2 times the radius. This is 2r. This is also 2r. Meaning that, or they're actually given radius 1. So 2, 2, 2 actually. 2, 2, 2. So it's an equilateral triangle. Meaning these are all 60 degrees. And we know the height of an equilateral triangle is root 3 by 2 times the side length. So root 3 by 2 times 2, which is square root 3. So this height of the equilateral triangle is square root 3. So this is square root 3, 1. So 2 root 3 plus 1 is the radius of the large circle. So we do 2 root 3 plus 1 squared is equal to 13 plus 4 root 3 pi. So pi. And then we can see that the area of all of the white regions is just going to be equal to 13 times 1 squared pi, which is equal to 13 pi. So we subtract them out, we get a simple answer of just 4 root 3 pi. Cool problem, right? Because we draw the useful radii, we extracted the information of this equilateral triangle, the height, and then we found the overall radius of the whole large circle. And that's how we did this problem. Okay, now let's take a look at this problem. It's going to be the last problem for our circle section. Okay, so this is the most tricky problem in this section. So we have this weird hexagonal figure, and we want to find this area. This is 2, 2, 2, 2, 2. I want to find this weird region here. This weird region. So how can we do that actually? What are some ideas? How can we think of finding the area of this weird red-shaped region? It's not like anything nice. It's just the semicircle curved in. Do you have any ideas on how we can try to find this area? Yeah, someone had a good idea in the chat. Basically, this is basically a hexagon minus these weird curved areas. So essentially, it's almost a hexagon, except we're subtracting these regions here. These regions here. These six of these, curved regions here. I don't know what to call them. Loons. It's called a loon, actually, but yeah. So how can we do that? Well, firstly, how do we find the side length of the hexagon? So how can we find these areas of these weird segments? So firstly, how do we find the side length of the hexagon? Do you have any ideas on that? Yeah, there's actually many ways to do this. There's not one way. There's actually many ways to find these areas of this. So firstly, how do you find the side length of the hexagon? Well, it's a common property that a hexagon can be divided into 6 equilateral triangles. So if you think about this blue shape, it's simply half of an equilateral triangle. So since this is half of an equilateral triangle, half of a hexagon. I don't know why I said triangle. This trapezoid is half of a hexagon. And we know the hexagon, you should all know this, that a regular hexagon can be divided into 6 congruent equilateral triangles. But since there's only half of it, we're only dividing into 3 of these triangles. So now we have 3 equilateral triangles. We split this half hexagon, I'm just going to call it a half hexagon, to 3 equilateral triangles. But we know that the sum of both of these segments is 2. So they both have to have a length of 1. Meaning that this will have a length of 1, 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 and this will have a length of 1. So the area of the hexagon is just going to be root 3 by 4 times 6, which is 3 root 3 by 2. And then we can see that the area of each of these regions, how do we find that out? How do we find the area of these curved regions here? So a common strategy is to find the area of these kind of weird curved regions to, again, form nicer areas. We discussed way back in the AMC classes. To find the area of these weird regions, we want to find the area, look at the area of nice regions, and subtract other regions we know how to find. So what's a nicer region we can look at other than this weird curve region that this weird curve region is actually part of? So what's the region that this weird curve, this green area, is part of? So what is this part of? What kind of segment can we actually use it as a part of? Yeah, exactly. We can look at it as it's a part of this like equilateral triangle here. We can say that this triangle, this arc, I should say, this arc has the area of, well, we know that the side length of the hexagon is 1. We know each of these lengths is 1. We know 1, 1. So the area of this arc is just simply, this is 60 degrees. It's an equilateral triangle, right? 60. It's going to be equal to 60 over 360 times 1 squared pi. So this is going to be pi over 6. And the area of the equilateral triangle is then going to be equal to root 3 over 4. So the area of the segment here is just going to be pi over 6 minus root 3 over 4. So that's the area of one of these loon regions. Okay, so now what? Now we find the area of one of these green regions that I mentioned earlier. Now, how do we finish? From here, it's pretty easy. Since the area of one of these regions is just going to be this quantity, we just do 6 times this. And this is equal to pi minus 3 root 3 by 2. And then the answer is just going to be 3 root 3 by 2 minus this quantity, which is, let me just see. 3 root 3 by 2 minus pi minus 3 root 3 by 2, which is 3 root 3 minus pi, which is this D choice. So really cool problem, involves some cool ideas here. The main takeaway is that, firstly, we see that this is almost a hexagon. Hexagon minus these 6 of these regions. Next step is, what nicer shape includes these regions that we can easily find the area? And that was the arc, 60-degree arc. We found the area of the 60-degree arc, subtracted the area of the side length 1 equilateral triangle, Find the area of that weird shape, the weird curved shape. Subtracted 6 times that from our hexagon area to get our answer. Okay. Oh, we're already at PowerPoint. So basically, PowerPoint states that if you have a circle and then you have two tangents, this PowerPoint actually has multiple kind of parts to it. So the first part of PowerPoint is that in a circle, we have the two tangents are going to be equal. So these two tangents are going to be equal. And another good property, this is not actually part of PowerPoint, but basically, if you have a circle and then you have a tangent, if you connect the center of the circle to the tangent or opposite line, it's 90 degrees. Okay, so we know this is going to be 90 degrees. Just like I've shown in the figure, if we draw this line, it's going to be 90 degrees. Okay, so now, if we know these are going to all be 90 degrees, we can see that in tangents, it's going to be 90 degrees. So PowerPoint states that two tangents are equal. And similarly here, we have that two tangents will be equal in this case too. So the two tangents are equal, they form 90 degree angles. Both very powerful properties. The next part is a PowerPoint is actually the harder part of it. Basically, it states that PA times PB is equal to PC times, let's make that red, times the whole segment here, PD. So the product of the green and blue lengths is equal to the product of the red and pink lengths. Basically, PA times PB is equal to PC times PD. And we can see that PA times PB is PC times PD. Very powerful property. And basically, also we know that this quantity is also going to be equal to PT squared. So it's also equal to PT squared. But a very common mistake in PowerPoint is that, a very common mistake that I have made before earlier, a few years back, is that I thought, okay, PowerPoint means PA times AB is going to be equal to PC times PCD. That's wrong. Be very careful of that. Product of segments is not equal. It's the whole thing. And the good way to remember this is that all your terms should have P in them. All your terms should have P in them. It should not be PA times AB. It should be PA times PB. And PowerPoint also holds true for a circle on the inside. If a circle on the inside, we have is that AP times PB is going to be equal to PD times PC. And there's actually a really cool proof to the PowerPoint theorem, which I'm going to quickly demonstrate for you. So basically, the reason this is true, let me just write it out. PA times PB is PC times PD. There's a really instructive proof, a nice and instructive proof of the PowerPoint theorem. So in order to prove PowerPoint, actually consider drawing these two lines. If we draw these two lines, we can see that these angles are equal. Or I should explain why those are equal. So we can see that this angle is simply equal to half of this arc, which is equal to this angle here. So these two red angles are equal. Similarly, we also have that this blue angle is going to be equal to half of this arc, which is also equal to this angle here. So you can see that the red angles are equal, the blue angles are equal, and if two angles are equal and two triangles, what do we know about them? We know that they are similar. Okay, so now that we know they're similar, what does that tell us? That tells us PA over PC equals PD over PB, telling us that PA times PB is equal to PC times PD. Keeps getting erased, I don't know why. But that's basically what PowerPoint is. Okay, now let's take a look at some simple problems using PowerPoint. So basically, if you have a triangle ABC, AB is 96, AC is 97, what can we do? Well, or let me draw it the other way actually. Let's just say that we have a line, AB that's 86. Let's draw a circle through it. Maybe I should draw the circle first. And then we have this point A in the middle. We have that, we choose a point AB here. And then we choose a point AC like that. Okay, this is what we have. We have that. AB, AC, B, A, 86, 11. A circle with center A and radius AB intersects BC at B and X. And moreover, BX and CX have integer lengths. What's BC? So what do we actually know about this diagram? So whenever we're dealing with secants and tangents, power of a point is a good sign, a very good sign. So what we can see is that the power of C is equal to 11 times, power of C is equal to BC. Well, let's just extend this point to D. So we can have the power of C is equal to BC times CD. It's also equal to CX times CB, because that's PowerPoint theorem. So what is BC? BC is 11. And what is CD? CD is 11 plus 86 plus 86. This is 86, radius of circle, right? So 11 plus 86 plus 86 is 203. So 11 times 203 is equal to the power of C. And notice that 11 times 203 is simply equal to 11 times 7 times 29. Okay, so now what can we do? Now we can see that if PC times CD is equal to 11 times 7 times 29, we have that CX times CB. How can we find CX from CB? Well, CX times CB is just going to be equal to 11 times 7 times 29 too. So how can we actually find the lengths? Oh, it looks like I have two B's in the diagram. I'll change that to an E, or let's call it Y. Because that changes things a lot. But then I'll say that C, sorry for being confusing with that. So basically then we have that CY times CD is CX from CB. And CX, CY is just 11 times, it doesn't really change anything though. Which is 7 times 11 times 29. And that's also equal to CX times CB. Well, what is CX and CB? Well, it has to be integers, right? Integers lengths. Well, notice that if you have a circle and they have another point, this distance will always be minimum when at this point here. So you can see that in a circle, this segment, all these other segments that connect the any point to any point on the circle, the minimum distance segment is the one that passes through the diameter of the circle, right here. It's a very useful property. It's going to be minimum there. Or even if you didn't know that, you can just use common sense and see that XC is probably going to be bigger than YC. So XC has to be bigger than YC. Now what are the possibilities? Well, notice that what are the factors of 7 times 11 times 29? The factors are 1, 7, 11, 29, 77, and then there's some other ones that I won't bother listing out. So we have 8 factors of 7 times 11 times 29 by our factor formula. So which one of them can work? Oh yeah, sorry. This should be, yeah, you're right. This should be equal to 11 times, 11 plus 86 times 2 is 172. So 11 times 83, 183, which is equal to 3 times 11 times 61. Yeah, sorry. So basically, it's still a similar idea. We have 1, 3, 11, 33, 61, right? So from here, we can see that the possibilities for CY again has to be greater than 11. So these 3 possibilities are ruled out. So the next possibility you can try trying is 33. So if CX is 33, we can see that CB will have to be 61, which means that if CB, this actually means that XB is going to be 28. Sorry about that issue. Basically, the idea from here is that XB will have to be 28. So this actually does work from here. So just to summarize the key steps, we use power of a point because we're dealing with tangents and secants. And tangents or secants are always a good sign to use power of a point. So from here you can see that if CX is 33, CX will have to be 61. Because 33 times 61 is And we can see that 61 actually does work. Because if this is 61, then this is 28. And to any chord in the circle has to be less in length than the diameter in the circle. So we can see the 33 does work. And just to show you why 61 and the other ones won't work, it's because that if it's 61, then it's going to be greater than half. So this is going to be, then if it's 61, then CX is more than CB, which is not possible by your diagram. So the answer has to be 61. Okay, so let's take a look at the next. Let's look at the break. So now we're going to be raffling 2 Wolfram subscriptions today. And today is our last class, class 8. So you can check out this raffle form that will be put in the chat. Okay, so now let's get back to this problem. It's a really cool problem. So basically, we're given is that we have two circular arcs, AC and BC. So they have two circular arcs, and they have their centers at AB, at B. So basically, we have these two circular arcs. Oops, should unselect that. These two circular arcs, and that we're going to connect these two lines. We're saying that circular arcs AC and BC have their centers at B and A. So let's look at circular AC has the center as B, meaning that CB is equal to AB, right? Because basically, since it's a circular arc, all these different segments are all going to be equal, right? Or I'm just going to erase some of them because we don't need them right now. And similarly, because we know that A, C, and B are on circular A, we have that all these segments are equal. These two segments are going to be equal because they're both radii of the circle, meaning that this triangle is equilateral triangle. Really cool, right? Because we have that AC, we know that AC is equal to AB, and we also know that BC is equal to AB. So if AB is BC and AB is AC, then AB is equal to AC is equal to BC. So three sides are equal. And that tells us that since all three side lengths are equal, we can see that so since basically we have AC equal to AB, basically since points A and C are on circle with center B, we have that BA is equal to BC. And since we also have arc BC on with center A, we know that AC is AB. So if AC is equal to AB and BC is AB, then all three segments are equal. Okay, so if all three segments are equal, what does that mean? That means it's an equilateral triangle, or all three angles are 60. Okay, so if all three angles are 60, and this is 12, then what do we know? Well, let's call this radius R. Then we can see that R squared, 2 pi R, 2 pi big R, let's call it. So we have that 2 pi big R times 60 over 360 equals pi R over 3, which is 12. Meaning R is equal to 36 over pi. And if R is 36 over pi, we can see that this is going to be 18 over pi. This is equal to 18 over pi. Then what do we know? So what can we do from here? If these are both 18 over pi long, we can see that this segment here is just going to be equal to 18 over pi root 3. Remember 30, 60, 90 triangles. Or actually, I don't know why I'm marking that. That doesn't actually give us much useful information. So we can actually get all those lengths with these equilateral triangle in mind. But that doesn't really help us. So now, what are any ideas? What are any ideas of what we can do in this problem? You can put your ideas in the chat. Let's see what ideas you have on how we can actually proceed from here. So we already got one useful fact that each of these segments is 18 over pi, and the radius of this big R is 36 over pi. What else can we get really? What other information do we know? I'll give you a hint. It's something to do with the topic we just learned about. Any guesses on what we can do? Yeah, PowerPoint. Exactly. We can use PowerPoint. And the reason is we can use PowerPoint is because we've got tangents. And tangents are good signs. We've got tangents and we've got tangent lengths. Tangent and tangent lengths, those are good signs to use PowerPoint. So then we know that tangent squared, 18 over pi squared. Oops, that's way too thick. 18 over pi squared is 324 over pi squared. And 324 pi squared is also going to be equal to the product of these two lengths. Product of this, or let's try this. The product of this, and so now that we have the power of A, what other secants can be used? Can we get information out of? Well, notice that we know that A times this green segment times this red segment here is going to also get equal to 324 over pi squared. So let's call this point P. Then we have that PA times A. Let's say call this point, don't want to reuse variables like I did last time. PA times QA is going to be 324 over pi squared. Actually, let's let this length be x. Let's let this be x. Let's call this little r. Little r is what we want to find. Little r, the radius of the small circle. So we have that x times x plus 2r. Remember, the whole length AQ is equal to 324 over pi squared. Right? So now we have one variable in terms of x and r. We technically need some more information that we haven't extracted yet. So what more information can we actually extract from our figure? What more information do we know? Well, the only more information so somehow we have one variable. We want to find another equation. So any ideas on what other equation we can try using here? Again, it's something to do with the information we already know in the problem. Information is going to be related to the information we calculated in the beginning of the problem. That big R is 36 over pi. That this PowerPoint equation is true. What can we actually use? What we can actually use is we can see that since AB has a length of 36 over pi, well, if you consider here that the arc's length, this blue segment here is an arc of a circle with center A. So in this arc, since AB has, let me just clear it up for some avoiding of confusion. So in this arc, we can see that this whole length here is going to be 36 over pi 2. This blue segment is also going to have a length of 36 over pi. The reason is because AB is a length of 36 over pi, and AB lies on a circle of radius A, right on the same circle as radius A. AB is the radius of the circle A, and A, whatever this point is here, also lies on a circle of the same radius. So that means AB is equal to A times this red point. So they're both equal. So that means the red point is going to be 36 over pi. And we said that this is x, this is r, this is r. So we know that x plus 2r is actually just 36 over pi. So we know now we know that x times 36 over pi is equal to 224 pi squared. We divide by 36 over pi to both sides. We get x is equal to 9 over pi. Okay, so x equal to 9 over pi. We want to solve for r. Pretty easy. We just substitute it back into our equation. X plus 2r is 36 over pi. We get that if x is 9 over pi, 2r is 27 over pi, which means r is 27 over 2 pi, which means the circumference of a circle with radius pi is just going to be 2 pi r. Cancel, we get 27. So r is 27. The circumference is 27. Then that's the answer. This problem was really cool application. Basically, the idea was we first use the fact that they're on a circle to get that it's an equilateral triangle. Then we saw, okay, 18 over pi, 18 over pi. Now what can we do? Now we're stuck almost. But we're not. Tangents, secants, sine of using power of a point. We see the tangent, we think the power of A is 324 over pi squared. What can we do with this information about the power? Well, the only secant that seems logical to look at is A to the red point. This line here, this segment here the segment here has to also be somehow apply power of a point to this. So we just do x times x plus 2r is going to be 324 over pi squared. So we see that, okay, x plus 2r is 36 over pi. It lies in the same rate. It's the same as the radius AB on the circle. So we substitute that back. We get x is 9 over pi, which means that we see that r will then be 27 over 2 pi. We find the circumference of the circle easily from there. The key idea being, no one to apply power of a point, number one. And number two, when you're stuck, you look at the information you don't know. I mean, we haven't used fully. We've not really used too much about the information of the arcs, other than the fact that it's 36 over pi. So try to use that again. Somehow get that this length is also 36 over pi. And that was a very special property of this problem. Okay. So now we're going to explore cyclic quadrilaterals. We already discussed this in detail in the AMC math counts class. Basically, in a cyclic quad, the sum of the opposite angles, the sum of the pink angles is 180, and the sum of the red angles is also 180. Cool property. And we also know in cyclic quadrilaterals, since it's inscribed in the circle, a very special property of cyclic quadrilaterals too is that if you draw these lines, we see that if this is x, this will be x. If this is y, this will be y. The reason is it's just an inscribed arc theorem. It's pretty easy to see that this is double of this arc, and this is also double of this arc. And we can also see that this is double of this arc, this is double of this arc. So two important properties of cyclic quadrilaterals. And actually, there's a really nice proof for the cyclic quadrilateral property, and I'll just briefly describe it. Basically, the reason the sum of the opposite angles is 180 is because this arc, let's just call this arc here to be 2q. Let's say this arc is 2q, right? And then let's say this arc is going to be 2p, right? Because if this is p, this angle is half of the arc angle. So this will be 2p, this is 2q, meaning that 2p plus 2q is 360, or p plus q is 180. So really nice proof of the cyclic quadrilateral property, nice and simple. And that's why the sum of the opposite angles is 180. Okay, so now let's take a look at some basic cyclic quad problems. In the circle, diameter EB is parallel to DC. Parallel. Let's mark that in our diagram. AB is parallel to ED. AB is parallel to ED. So these are going to both be parallel. Okay? That's also useful. And AEB and ABE in a ratio of 4 to 5. So let's call this 4x and 5x. Okay? Okay, now what do we know? EB is a diameter. What do we know about angles in a diameter? Angles in a diameter are 90 degrees. Very useful property. You should definitely know it. We already discussed that in the beginning. 90-degree angle. Okay. So we know this is 90. That means 4x plus 5x plus 90 is 180. And that means 9x is 90 or x is 10. We substitute that back. Let's write 40, 50 here. 40 and 50 here. Okay, so since these AB is parallel to ED, we see that if you think of this, the Z-shaped pattern, we can see that 50 will have to be equal to 50 here. Because of the Z-shaped pattern, we see that these angles are going to be equal. This angle is going to be equal to this angle. And if these two angles are equal, because of the parallel line property, I think it's called alternate interior angles, then that gives us some more information to work with. And now what is the other property? EB is parallel to DC. How can we use that? Well, exactly. That means angle EDC is 130 degrees. Because if they're parallel, I think it's called same side interior angles. The sum of the green angle and this EDC, it has to be 180. So it has to be 130 because they're supplementary angles on the outside. And now you might be stuck. What can we do now? How do we find the angle of BCD? How do we find the angle of this angle and this angle? How can we do that? Any ideas? So we already used one property, and we have these various points in a circle. We have these 5 points in a circle. We have so many points in the circle. We already used the condition of the triangle, of the 3 triangle points being in a circle. What else do we know? BC is not parallel to EA, so EBC actually won't be 40. BC is not parallel to EA. It's not given anywhere in the problem that BC is parallel to EA. So it's not actually going to be. Yeah, someone mentioned in the chat, BECD is cyclic. Exactly. BECD is a cyclic quadrilateral. This is a cyclic quadrilateral. And you might be thinking, yeah, but how would I randomly just think that, okay, this is cyclic quadrilateral? The key thing is, whenever we have a bunch of points on a circle, you always want to be on the lookout for a few points, like 3 points for a triangle, 4 points for a quadrilateral. A circle, when you have points, be on the lookout for triangles in the circle and quadrilaterals in the circle, because then you can get angles about inscribed triangles and inscribed quadrilaterals or cyclic quadrilaterals. And cyclic quadrilaterals are extremely helpful for angle chasing problems. Because now that we know this quadrilateral is cyclic, what can we do? Well, from here it's actually pretty straightforward. If this is 50, this has to be 130. That's the answer. So I think the real jump in logic here is that even though it's actually quite hard to spot that, oh, this is cyclic, because there's just so much other stuff going on in the diagram. Like if I erase this triangle, I'm sure many more of you would have realized that it's cyclic. Just that this other part of the diagram is kind of hiding the real deal, the cyclic quad. So if we just erase this part, it might be more clear that, oh, it's just a quadrilateral in the circle. So you'd always assume when you have points on a circle, there's triangles inscribed. There's quadrilaterals inscribed. Useful properties. Inscribed triangles in circle gives you useful properties about the circumradius, about angle conditions. Inscribed quadrilaterals in circles, again, those also give you different properties. They give you properties about the angles, properties of the arcs. So these are both very useful. So even though there's just one quadrilateral in the midst of all this other stuff, in the midst of A and AB, be on the lookout for quadrilaterals, cyclic quadrilaterals, whenever you have points on a circle, and same thing for inscribed triangles. Okay, now let's take a look at some more challenging questions. So, triangle ABC is an isosceles right triangle with AB equal to AC equals 3. Let M be the midpoint of the hypotenuse BC. So midpoint. So immediately you can see AC is 3, AB is 3, CB will have to have a length of 3 root 2 by 45, 45, 90 triangle, or it's just equal, isosceles right triangle. An isosceles right triangle is always going to be 45, 45, 90. So 45, 45. This 3 root 2, meaning that each individual part is going to be 3 root 2 by 2. So now what? Someone asked, how do you know when it's a quadrilateral cyclic? You know when a quadrilateral cyclic, either if the problem literally tells you it's cyclic, like it does now, because if the problem literally tells you it's cyclic, then you know it's cyclic. But more often, you know a quadrilateral cyclic because there's either 4 points on a circle, maybe it might be hidden, but whenever there's 4 points on a circle, a quadrilateral cyclic. If the problem says it's cyclic, then it's obviously cyclic. And also, the more less obvious thing is that if the sum of the opposite angles is 180 and if sum of any two opposite angles is 180, and another thing is that if the sum of two opposite angles is 180, then you know it's cyclic. And also, if you have these kind of diagonals here, if you know these angles are equal, then you also know it's cyclic, or these angles too. So that's when you know it's cyclic. So cyclic, in this case, we are left the work of that. It literally tells us AMI is cyclic. So no work of finding cyclic quadrilaterals. The problem tells us, but this won't be the case for most problems. Okay, so now we are already given it's cyclic. So now instead of using the properties to figure out cyclic, we use it cyclic to figure out the properties. So what can we do with this cyclic quad? What do we know about cyclic quads that can be useful here? Yeah, someone mentioned it. Angle M is right. There's a right angle. IAE, 90 degrees, plus IME has to also be 90 degrees in order for the sum to be 180. It is actually useful, very useful in this problem. So now that we know this is 90 degrees, now what can we do? Is this it? Is this all we know about the cyclic quad? So basically, we have this is 3, the whole thing has to be 3 root 2. And then this will have to be 3 root 2 over 2, 3 root 2 over 2. And like I was mentioning earlier, we're already given the quadrilateral is cyclic. So if the quadrilateral we know is cyclic, if you know the quadrilateral is cyclic, then, well, we can use angle chasing conditions. So remember in cyclic quadrilaterals, the sum of the opposite angles is 180. So if this is 90 degrees, then this will also have to be 90 degrees. Yeah, we'll actually talk about Ptolemy's theorem later, but I'm pretty sure, yeah, If Ptolemy's theorem is true, it's cyclic. Okay, so from here, what can we do? Well, from here we can see that is this it from cyclic quadrilateral properties? What other cyclic quad properties do we have? So is this it? We know the sum of opposite angles is 180. Is there anything else we know about this diagram? Like I mentioned earlier, there's two cyclic quadrilateral properties. We use one of them. How can we use the other? So what's the other cyclic quadrilateral property? The other cyclic quadrilateral property is that if this is the angle A, then if you draw this line, it's also going to be an angle A. So this angle is going to be A. This is B. This is going to be B. Right? That's another cyclic quad property. So now what do you see here? This is actually somewhat of a hidden thing. What do you see? This is A. This is B. The median is here. What do you see? Does anyone notice anything about this? Yeah, I guess you could inscribe it in a circle, but there's really no need to. If it makes it more clear, I can just draw a circle around it. But you don't, even though quadrilateral cyclic, that doesn't mean there necessarily has to be a circle around it. But I'll just draw it if that, oops, that was not good. I'll just draw it for the sake of it if it makes it a little bit more easy to understand. Don't think I go to a circle, but at least it shows it is a circle around it. Yeah, A plus B is 90. We know that. And what else do we know? Exactly. We know A is equal to B. Because if you notice here, if you consider this triangle here, and this triangle here, they're actually congruent because of hypotenuse-like congruence. Because the hypotenuses are equal, the hypotenuses are both 3 and 3. The hypotenuse is 3, hypotenuse 3, legs are both the same, 2. So their true triangles are congruent, meaning that A is equal to B, because the angles are equal. So A is equal to B, A plus B is 90, so A equals B equals 45. So now we can substitute that back into 45. So these are both 45 degrees. Now, how can we find length of CI? From here, I'm just going to erase the whole diagram because we don't need it anymore. And I just want to make it easier to understand. I'm only going to leave the parts we actually need. So now we know, so 45, 45, 90. We know that A is equal to 45 and B is equal to 45. So it's a 45, 45, 90 triangle in the middle on the outside too. So from here, what can we do? From here, we can see that we still haven't used information that EMI is area 2. So if you know that, let's say IM has a side length of x. So if IM is side length x, then we know that x squared by 2 is equal to 2, meaning that x is equal to 2. So this is both going to be 2. And similarly, if you know IM is 2, let's say CI is some length y. Now, in order to find the length of CI, we can just use the law of cosines. So you can see that y squared plus 3 root 2 by 2 squared minus 2y times 3 root 2 over 2 times cosine 45, which is root 2 over 2, is going to be equal to 2 squared. And now what can we do? Now it's pretty straightforward to solve the problem from here. It's actually pretty straightforward to solve the problem from here. All you really need to do is you just need to simplify this expression and solve. And let me just do that really quickly. Y squared plus 3 root 2 over 2, which is just going to be equal to 18 over 4, so 9 halves, minus, and so we have some terms canceling here. So we're left with minus 3y equals 4, meaning that y squared, maybe I should write a little bit smaller. Y squared minus 3y plus 1 half is 0. Or y equals to 3 plus or minus the square root of b squared minus 4 times 1 half times 2 over 2. I don't know why I underlined y. And then this is going to be 3 plus or minus root 7 by 2. But we can actually see that it cannot be 3 plus root 7 by 2. Because that's too big and also does not satisfy the form the condition that our answer does. We can actually see clearly that if CI is going to be that length, then the conditions won't actually work. And also, anyways, it asks for, there's actually multiple possible values of CI, 3 plus root 7 by 2 and 3 minus root 7 by 2. But the one that satisfies the problem's condition is A minus root B by C. So we see the answer has to be 3 minus root 7 by 2. So the answer is 12. That's the solution for this problem. So basically, the thing is that the main idea, this is a really interesting problem. We have 3, 3. What we did is we said, okay, cyclic quadrilateral. What do we know about them? Opposite angles, sum to 180. What else do we know? These angles, 45, 45. We're going to say A. We basically just did, this is A. This will be A, B, and this will be B. And then from here we saw that, okay, wow, these triangles are probably congruent. We see that hypotenuse-like congruence, they're congruent. Means A equals B, and the sum is 90, so A and B are both 45, meaning that A and B, IME is a 45, 45, 90 triangle, and IM is 2, ME is 2, and then we see that y squared plus 3 root 2 squared, but 2 minus 2y times applied law of cosines, with our side length IM2, we solve this quadratic, we get an answer, and that's it. The key idea being, extract all quadratic properties of a certain shape, not just some certain properties, because even though the sum of opposite angles 180 is very helpful, we have to use the other property too, that the angles are going to be equal. So you have to use both properties. Same thing with, like, just like I said in the beginning, similar triangles give us two properties, angles and sides. Cyclic quadrilaterals also give us two properties, the angles in the side and the sides. And as we'll explore, they actually give us a third property, Ptolemy's theorem, which states that the product of the diagonals is the sum of the product of the opposite sides. So basically, the product of AC and BD is equal to the product of AB plus times CD plus the product of AD times BC. Very powerful theorem. Basically, sums of opposite sides is equal to the product of the red diagonals. Okay? So now, this is actually our last problem for today. It probably will be. So basically in this problem, we've got a quadrilateral inscribed in the circle, and the circle has radius 200 root 2. Just erasing that line because we're not there yet. So the radius of the circle is 200 root 2. These are all, should write in red, 200, or let's use this color here. Forgot to do this. 200, 200, 200, right? And we know that each of these radii are all going to be 200 root 2. 200 root 2, 200 root 2, 200 root 2, 200 root 2, right? These are all radius of the circle. Okay, so what can we actually do to find the length of this fourth side? This fourth side, AD, seems to be completely out of place here. AD is just some random side length in the midst of this whole diagram, right? So actually, there's actually one solution that does directly find AD, which basically does that you assign values, you just assign values to angles, you say this is theta, 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 and then you do some crazy sine and cosine stuff and use a sine triple angle formula. I'm not going to go into that solution, it's really complicated, but there's actually a much easier way to do this. So AD, the key insight is that AD is just a length that seems completely out of place. AD is just an out of place length. It's not really related. I mean, we have information about AB, BC, and CD, and AD is just at the bottom there. Not really. We can't really use 200, 200, the lengths of AB, BC, and CD at the top here, when AD is just at the bottom there. So somehow we don't really know how to find the length of AD directly. So a key strategy is that to find something, a length of something that's hard to find, try to find the length of something that's easier to find. So the insight here is that AD is hard to find. So instead, when you have a quadrilateral inscribed in the circle, you can actually use Ptolemy's theorem. By Ptolemy's theorem, the product of these red diagonals is equal to the product of 200 and AD and the product of AB and CD. So basically what this says is that AC times BD is equal to 200 times AD plus 200 squared. Right? This is Ptolemy's theorem. Product of 200 and 200, AB and BCD, is product of BC and AD, which is 280, and which is equal to the product of the red diagonals, AC and BD. And BD is equal to AC by symmetry. So it's just going to be equal to AC squared. Okay, so we know AC squared is 200 times 80 plus 200 squared, right? Okay, so if AC squared is 200 times 80 plus 200 squared, what else do we know? So what else do we know, really? So we can see that if we somehow find the length of AC, we can then find the length of AD. And the reason we think of doing this is because AC is a much more manageable length. AC is not just in the midst of there doing nothing related to our whole other diagram. AC's connecting points A and C. It's related to our whole diagram. It has altitudes in ABC, ABO. It just gives us so much more information than this side length AD. So now the question becomes, how do we find AC? Yeah, it's AC times BD, but BD is equal to AC by symmetry. So it's just equal to AC squared too. So basically, how do you find AC now? It's a real question. And again, there's also another really bashy trick solution where you let this be an angle and you use double angle formula, and that actually does work. So what else can we do instead of doing that? Because I don't want to explain that. What else can we do? The thing is, AC is, again, some length that can be easily transformed into easier length. Consider these two lengths, x and x. They're both half of AC. So if we find the length of x, we find the length of AC. And so then here, we can easily find the length of x. We can find the length of x. The length of x is just going to be equal to, well, what's the area of the triangle? The area of the triangle. How can we find the length of x? Well, notice that the length of x, you have the 200 root 2 times x divided by 2 is going to be equal to the area, which is, what is the area of the triangle? The area of the triangle is just going to be equal to 100, 200 root 2. This is going to be 100 root 7. So the area of the triangle is just going to simply be 10,000 root 7. So 10,000 root 7 is the area of the triangle. And if the area of the triangle is 10,000 root 7, 200 root 2 times x divided by 2, area of the triangle, we can cancel the terms. We get 100 root 2 times x is 10,000 root 7, or x is 100 root 7 by root 2. Okay, so from here, we see that x is simply equal to 50 root 14. So x is 50 root 14. So if x is 50 root 14, then AC is 100 root 14. And if AC is 100 root 14, now what can we do? We apply Ptolemy's theorem to our equation that we already got. So we have the AC squared is equal to 14 times 10,000 is equal to 200 times 80 plus 200 squared. Or alternatively, or actually, let me just move this down so I can explain it in an easier manner. So basically, now we apply Ptolemy's theorem, and we see that this is just going to be equal to 200 times 200 plus 80 by factoring, right? And then from here, we can see that if we divide by 200 to both sides of this equation, we get 200 plus 80 is 700, or 80 is 500, and that's the answer. So the motivation behind the solution is that when we are dealing with the complicated length, we want to transform it to simple lengths. And AC, it's again hard to directly find because you have to use sine a little bit easier, but still harder to find AC. So instead of looking at AC that way, we see that AC, we notice that AC is perpendicular to BO. And since AC is perpendicular to BO, that tells us that AC is just 2 times the altitude, which then gives us more information. Someone asked, how do you know BO and AC are perpendicular? Basically, if you have a circle, and we draw any chord like this, and you draw the radius, and you draw the perpendicular bisector, it will be 90 degrees. And the perpendicular bisector of any chord always passes the radius. That's a very important property. So basically, the perpendicular bisector of the radius is always going to be the pass through the center of the circle. Yeah. It's a very cool property. And from here, the main idea was that we can intuitively see that these are going to be 90 degrees. And another good strategy is that if something seems true, see if you can try to figure out why it's true, and then you can use it in the rest of the problem. Because in this case, it seems like they're almost perpendicular, so you see that, yeah, it's going to be perpendicular by this property. And then from there, you see that, it's 2 times the altitude, and from there, it's easy finish. Thank you all for coming for this class. And I hope you enjoyed these series of 8 classes. And thanks to you for watching. Thank you for coming to this class. Also, again, make sure to download the free ebook containing all the important formulas and strategies for the upcoming AMC 1012, and good luck to all of you on the AMC 1012.